Good evening, everybody. Today, I will be going to present a lecture on lightweight cryptography and its cryptanalysis. So, this is the so let me start. Lightweight cryptography is very recent field which is standardized by NIST on 2017 only. So, in this talk, I will cover in four parts. So, first part is lightweight cryptography. Here I will give the definition of lightweight cryptography, present the development in lightweight cryptography, and block cipher design principle, stream cipher design principle, and crypto hash. In the second part, I will discuss understanding of cryptanalysis, where I will discuss attack models and some of the common attacks performed on lightweight cryptography and IoT security. And in part 3, I will discuss some advanced topic where we can do research on lightweight cryptography, and these topics and this solution does not exist in the literature in respect to IoT security. And in the fourth part, I will discuss Cryptool, a very good tool through which we can start our basic research in lightweight cryptography. So why we need lightweight cryptography? First of all, there are some hardware devices like sensor network in healthcare IoT, chip-based ATM card, RFID tags. All these have very less amount of memory. So in these devices, the conventional cryptography may not be possible. So we can use lightweight cryptography and protocols for providing security in these devices. Now, the basic definition of lightweight cryptography as per the NIST standardization of 2017, uh, the total implementation of the cryptography, that is algorithms and protocols, will be on maximum 2500 gates or up to 3000 gates, and to minimum the area and power consumption. The main goal of lightweight cryptography is to reduce the power consumption and also reduce the area. Now, some lightweight standardized algorithm in lightweight cryptography are DESL, data encryption standard, lightweight, present, Clefia, Siemens, SPAC, T, etc. If we compare a relative study, we can see that in lightweight cryptography, block size is maximum 32 bits, while in non-LWC, block size is 64 to 128 bit. In LWC, key size is 80 to 96 bit, and non-LWC, it is minimum 128 bit. And in round function, it is 4 to 32 rounds, and in LWC, it is 10 to 32 rounds. Now, hash function in LWC domains are existing hash functions are photon, family, quark, and hash one. And their studies like also this one in smaller size is 64 bits and number of messages 2 to the power 64. While in non-LWC it is 160 bits and number of messages 2 to the power 160. So stream cipher in the LWC exist are mainly grain, trivium, and Mickey. So this is a block diagram of the present lightweight cryptography. So you can see here only two in per round only two sub round is there, and this is the algorithm. I am not going to the details of this algorithm. I am giving the reference where you can find the details of this algorithm, how it is working. Now in lightweight cryptography, hash function is like that, where R and C are the constant initial values, and some permutations occurs, and message is broken into M0, M1, M2, and like that, and these are stored, and finally we get the hash values as C0 and C1, which is concatenated, and it is an example in the photon family of hash function. So basic round function, here we see that this is the basic round. So this is the round function of a single round function of photon hash function, and this is a trivium and grain stream cipher. So left side this one is grain, and right side this one is trivium. So here we can see that in grain stream cipher, one non-linear feedback register is used and one linear feedback register is used, which is gone through some function, and this hx is the non-linear function and gives the output bit. And in this trivium, the nonlinearity is obtained by using three linear feedback shift register. Now in lightweight cryptography, what will be the our study? What should be the our study? That are physical metrics. In physical metrics, area, memory, implementation time, energy. In the performance metrics, it is latency, throughput, power. Okay, so all this you can get through Xilinx ISA design suite, where you can simulate and do the VHDL codes of your cryptographic algorithms and protocols, and you can simulate and get all these results. And other security characteristic I will also discuss later. That is number of bits required, attack model, and sidechain attack. Now, the block cipher design principle is what is actually a block cipher? Block cipher is actually a pseudo-random permutation. The basic unit of block cipher is pseudo-random permutation, where we have a k bits, 0, 1 bits up to length n, and x of length l, series of 0 and 1 of length l, and we a pseudo-random number, what is y, which is a function of k and x, and which is length l. And block cipher is designed, and the final block cipher is obtained is strong pseudo-random permutation. So what is strong pseudo-random permutation? If we put the pseudo-random permutation in cascaded manner, uh, and we provide the same k here, and x is different, we divide the message in x1, x2, and finally we get the output y, which is 0, 1, and length of t into l. Okay, so this total one is strong pseudo-random permutation, which is basically a block cipher. And stream cipher is obtained through linear feedback shift register. So this is a linear feedback shift register. It is an example. So basically what is happening in the linear feedback shift register, in each clock cycle, one bit is got output, and any 2, 3, or 4 bits, depending upon your implementation, is stored and it's go to the input. Okay. Now, in designing stream cipher, we actually does not use linear feedback shift register. We use non-linear feedback shift register. Why? Because linear feedback shift register is easily broken by two attacks known as linear cryptanalysis and differential cryptanalysis. So nonlinear feedback shift register can be obtained in two ways. In this first way, we can use three or more linear feedback shift register and combine them to form a nonlinear feedback shift register. This is in the second way, where feedback shift register is the linear, but the output function, feedback function, shift register is linear, feedback is linear, but the output function is non-linear. So ultimately we get a nonlinear feedback. So what will be our nonlinear function? It may be x square or ax square plus bx plus c or 2 to the power x and like that. And designing principle of hash function are mainly of three types. One is pre-image resistance, which is called one-way function, such that one message m has only one hash value. Second principle is second pre-image resistance, which is called one-to-one bijective function, which tells that two messages does not have same hash value. And another one is collision resistant, which is the combination of pre-image and second pre-image. Okay. Now, mainly in lightweight cryptography, uh, hash functions are based on Mark-Ledy-Mark construction, where we broke the message and get input into the function hash function, and finally we get some finalization where compression can be done in it, and finally we get the hash value. So this is the end of my part 1. Now, to design a good algorithm, we need to understand the attack also, because understanding of attack is very much important. So basically all the attacks are done on these four types of attack models. So first attack model is ciphertext only attack or COA. So in the COA, only ciphertext are available, and intruder if analyze it to get the plain text or key. In the next attack model, non-plain text attack, the the attacker if has some ego have access of this encryption mechanism. So if had some pair of previous pair of plain text and ciphertext, and here when the new ciphertext is got, here when new ciphertext is got, so when new ciphertext is got, so we analyze this pair to get the attack model. So in the non-plain text attack, so we have previous pair which analyzed. Now in the chosen plain text attack, the attacker got access of the encryption oracle. So it encrypt its chosen plain text and get the ciphertext and then analyze the new ciphertext. In the chosen ciphertext attack, the attacker got the access to both encryption oracle and decryption oracle. So what is the basic definition of security? The Kirchhoff principle says that a crypto system should be secure if except the key, if everything is known, then attacker does not guess the plain text. Now Shannon reduced it to a mathematical formula. It says that probability of finding a key should be 1 by total key space. And any secure cipher must have a key space that is not vulnerable to exhaustive search. It is sufficient key space principle. Now in modern cryptography or in lightweight cryptography also, we have computational security, where the assumptions are adversary knows the computationally bounded, adversary is now computationally bounded. He is allowed to learn the plain text with negligible probability. Adversary is also efficient and is allowed to break cipher with some probability. So definition of computational security is that cipher is computationally secure if attacker can find the actual plain text or key or both having actual ciphertext with above condition in a few lifetimes. So we do not need an everlasting security. We need a lifetime security. That means, suppose for a critical application like in military encryption processes, if the algorithm gives the security of 30 days or 1 month, it is enough for them. So this is the definition of computational security. So what are the attack? Main attack is brute force attack. Here you can see the lifetime of 1 to the power 28 through 128 bits is this much. Okay. Second one is very interesting attack on lightweight cryptography or hardware devices are power and time analysis. So we measure the power over time to perform the side channel attack. It is also known as implementation attack. So it is an example, it is a square and multiplier example uh, compute, where we compute, where we compute x to the power c mod n, and the algorithm is we break this c in a series of bits, which is equivalent to the binary numbers, and we perform from MSB to LSB. The first thing is we do the z square, z is 1, z square mod n, and if this bit is 1, then we perform z into x mod n. So if we go to this example, let we have to find the value of 9726 to the power 3533 mod 1141. So first we break 3533 into this series. So it is this basically binary value of 3533. Now find 1, so we are doing square and multiplication both. When it is 1, we are doing square and multiplication. Then performing the mod of 1141. And when it is 0, we are only performing the square function. And the result is obviously mod of 1141. So if we do the side channel attack, we can see that if there are one spike, that means we are performing square. If there are two spikes consecutively, so that means we are performing square and multiplication. So for square, the value is what? 0. And for square and multiplication, the bit value is obviously 1. So this is an interesting attack through which we can guess the value of that power operation. Okay. So if you recall RSA, this one is private. So you can find this value by this side channel attack. So this is the end of part 2. Now I will discuss some of the advanced topics which are also which solution, feasible solution till does not exist in domain of lightweight cryptography and IoT security. So first is ID-based encryption. So what is the basic idea, basic philosophy behind the ID-based encryption is that encryption is done through the ID of the receiver. So in this example, we can say that this receiver ID is bob@b.com, email address of the receiver. So when Alice is sending a message to the Bob, he is encrypting the message with ID-based encryption algorithm using bob@b.com as a key, which is public key. And now how Bob decrypts it? Bob decrypts it by taking help of key generation center, where he gives his public key, and key generation center has some algorithm of key generation which gives private key to the Bob. So when the message comes from Alice, Bob decrypts. So this is the basic definition or basic idea behind the ID-based encryption. Next one is attribute-based encryption. So what is attribute-based encryption? Suppose you are going to send a message to a student of BTech 4th year computer science. So that group of students have some attribute is common. That group of students have some attribute is common. For example, their year, their branch, like that, and their degree, BTech. So when I am sending a message to that group of people, this message is encrypted by attributes of that group of people. So this encryption is also one-to-many encryption. So this is example of attribute-based encryption. Second one is homomorphic encryption. Homomorphic encryption is a type of encryption where actually a value is returned, not the ciphertext is written. So in homomorphic encryption, suppose Alice is sending a ciphertext of his message M, and which encrypted with private key of the Alice, and it sends to the server. Now Bob send a function f, and the server computes this function with the Alice ciphertext and send it to the Bob. The value is sent to the Bob, and this value is of course encrypted by private key of Bob. Now, what are the application of homomorphic encryption? The main application of homomorphic encryption is, suppose using a cloud computing service where you are asking for some service or some function what is not possible in your laptop. So you want to get the value of that function. So you give the value to the cloud server, and cloud server computes and give you back the value. So these types of applications are done with homomorphic encryption. So this is an example of homomorphic encryption. Suppose if a plus operator is the homomorphic function, then C1 is first ciphertext, C2 is second ciphertext. So final ciphertext of two messages will be the concatenation, adding of message M1 and M2 and then encrypting. So example of partially homomorphic crypto systems are RSA, Algol, etc. And fully homomorphic encryption are lattice-based cryptography or fully homomorphic encryption. Next one is called functional encryption. Okay. So in the functional encryption, it is a special type of homomorphic encryption. So in functional encryption, you can see that there are 4 steps. First step is setup phase, where master public key and master secret key are generated by the key center. Okay. And in the second phase, a key determination and algorithm create a secret key of that function using key determination and algorithm. Finally, encrypted the ciphertext this is the encryption. Third one is the encryption function, where master public key is used and the message and encryption is done to give the ciphertext. And finally, decryption is done with secret key of F and ciphertext result. Okay, so this is actually the value of F of n. So this is known as functional encryption. Now, one interesting application of functional encryption is that suppose we insert ATM card and our limit is 10,000 and we want to withdraw 12,000. Then ATM machine will give you a reply that enter lesser amount or your transaction is over 10,000 or 1 lakh. So these types of security mechanisms are obtained with functional encryption. Next one is very important, very interesting one is zero knowledge proof. So zero knowledge proof is an algorithm or it is a scenario where you don't have to give your total identity. Suppose when you are entering a movie house or theater, so you don't need to show them your voter ID card or your PAN card or your anything Aadhaar card. So you only need to show them the ticket. So this type of application are known as zero knowledge proof. So in zero knowledge proof, this is the last one is the zero knowledge proof verification algorithm, which gives you are authentic user or not authentic user. So it gives two output, true or false. Okay. Now this zero knowledge proof algorithm have three inputs. One is your proof, that is your database. You are showing your ticket, some number is there. Okay. Your seat number is there, date is there. This is called as proof. Next one is custom request. You are requesting the guard that please allow me for this show. So this is the custom request. And this is the proof logic. It is another algorithm which gives proof logic to zero knowledge proof verification. So what is the proof logic? When you are giving this your movie ticket to the gatekeeper, he knows something unique about that ticket, which is written there. So by using this, he can judge you whether this ticket is original or forged. So this type of algorithm, so these three are the input, and finally you are given true or false. So this is the end of the application is the same I have told you earlier, zero knowledge proof applications. So this is the end of part 3. Now last one is the Cryptool. Now last one is the Cryptool. So Cryptool is a very popular tool for cryptographic analysis. So you can access this Cryptool in this given link. Okay. So Cryptool have two versions, Cryptool 1 and Cryptool 2 for Windows, and J Cryptool is also available for Linux and Mac OS. And not only that, Cryptool has some interesting games, number shop, divider game, Sudoku, etc. Now in Cryptool, you can see that Cryptool 1 is available in 6 languages, Cryptool 2 is available in 3 languages, and J-Cryptool is available only in 2 languages. Now through Cryptool, you can perform many tests. So these tests are such as entropy, plotting frequency, histogram, n-gram, autocorrelation, periodicity, factorization of a number, attack on hash values, randomness test using frequency test, poker test, range test, serial test, and etc. So interesting fact is there in Cryptool, you have 400 algorithms implemented in the Cryptool. And also Cryptool have good documentation. You have every codes, you have the algorithm, you have the description. Now entropy. So first thing is you have to load your plain text in the Cryptool. Then you have to encrypt your plain text using your algorithm. uh, which algorithm you are going to study. So I have done here with this data encryption standard in CBC, cipher blockchaining mode, and this is my key through which we get the cipher text. And if you design your own algorithm, you have to just load it here by using this file menu. Then the analysis start. So basic definition of entropy is this one. So we call information content of mi is the log of 1 by pi. Pi is the probability of message I in this plain text, and the final encryption of the entropy of the total message is this one, minus p1 into log of p1 plus p2 into log of p2 and etc. plus up to all the message log. So you can find the entropy here. So for in this example, I have found 7.86 out of 8 entropy value. Now floating frequency is there. So floating frequency is defined as number of characters occurring repeatedly in 64 character long segment. So this is a graph you can obtain in the Cryptool of your floating frequency. Now again you can next one is you can got the histogram analysis. So I have used the SK values 0 to 255 of my plain cipher text. So this is the histogram. Then n-gram. Okay. So n-gram analysis. So n-gram is the how many 1 gram or 2 gram or 3 gram letter occurring in your cipher text or plain text. And histogram is basically special case of n-gram where n is 1. Okay, so this is an example of trigram. This is 2 gram diagram. So you can see that diagrams are he, in, on. Okay, so I have did the n-gram analysis with the plain text because plain text is basically a English language. Next one is autocorrelation, which we can define as correlation. We can define as C equal to A minus T, where A is the number of agree and D is the number of non-agree, and is the size of the documents. And autocorrelation is defined as A of T minus D of T. Autocorrelation of particular document is S of T and D of T by N. So here you can get the autocorrelation graph. Next one is periodicity. Periodicity means some number of text repeating or not, but it is different from n-gram because in n-gram you are getting how many times that your letter D, on, okay, these words are coming. And periodicity means if your some bits is repeatedly repeating or not. So in Cryptool you have either yes or no answer. So since it is an no repetition is found, so no periodicity is found, and if repetition is found there, they will give the details value. Again, factorization of a number is interesting application of the Cryptool. Suppose here factorization are done with this algorithm. So first you have to enter your value here, and you will start by brute force algorithm. If brute force fails, then this Byrant algorithm, then Pollard, William, and this way. So I have given a 1206, and Cryptool finds this factorization as 2 into this one 603. So it easily found by brute force. Okay. Now another example is prime factorization. So 11413, which I have given an example in the side channel attack. So I have given 11413 here. So we get the prime factorization of 11413 as 101 into 113. Now hash value. So you can also use Cryptool to find the attack on the hash value. So this is an attack which is done on MD2, because MD2 is not acceptable due to this attack. Okay, so you can see that in MD2, Cryptool can generate two message with same hash value. This one is the dangerous message. Please order a post and prepaid insurance scheme for Mr. Doggy, and this is my original message. Please order a typewriter. So both have same hash value on and digital signature using MD2. So it is one of the interesting tests you can perform in the Cryptool. Okay, this is another example of attack on hash value. Now you can also perform a randomness test, that your ciphertext or plain text is random or non-random. So you can frequency test. So it is done in this frequency test. So right means you have no randomness on yeah, your ciphertext is absolutely random. Okay, now next one is poker test. So poker test is basically this one, where 255, so 55 is 0.255, 55 is repeating, 0.5777 is repeating, 0.331, 3 and 3 is repeating. So this is the poker test analysis. The formula is given here. And here also I found this, my ciphertext is random using poker test. Next one is run test. So run test is basically how many ones or zero is running consecutively. So again, randomness analysis done with the run test. And next one is serial test. So serial test have some formula. Suppose n0 and 1 is the number of zeros and number of 1. N00 and 01 and 10 and 11 are the number of 00, number of 01, number of 10 and number of 11. Now summation of n00 plus n01 n10 and n11 equal to n minus 1, and the formula is this one. So it is basically similar to chi-square formula. So 4 by n minus 1 into n0 square plus n01 square plus n10 square n11 square minus 2 by n into this one, n0 square plus n1 square plus 1. So using this we can find this test is randomness test using this serial test. So here I have used plain text to see that actually plain text is English language. So English language cannot be random at all, because English language follows some grammar. So when I did randomness test of my plain text with serial test, so it is coming serial test failed, because this plain text is not random. So that is the end of my lecture. So I am not giving you a list of 20 or 30 references. only giving you the three references, which is very important to start your research on lightweight cryptography and protocols and consecutively IoT security. So first one is NIST standardization, which is done in 2017. You can access this one in this DOI page. Next one is very important, very good book, which is of Springer book, where you can have the good idea of IoT, and part 6 of that books contain lot of chapter on IoT securities. And finally, there is a project called known as Cryptech, which is cryptography technology guidance, specifically on lightweight cryptography, which is also made public on 2017. So, using these three references, you can start your work in this domain. Thank you.